And let me introduce our first lecturer, is Professor Yuli Nazarov, who is well-known expert in theory of quantum transport in general and superconductivity. And as we see, the title will be Quantum Transport in Superconducting Devices. So Yuli, please start.
Thank you. I'm pleased to be here, and in distinction from all other lecturers, I was asked to give really basic, comprehensive introduction to superconductivity, to quantum transport in superconductivity, and in addition to quantum properties of superconducting phase. Right? I will give these today 2 lectures. First lecture will be about quantum electrons in superconductors. There will be no quantum dynamics of superconducting phase yet. That will come in the second lecture. Right. As I mentioned, it's really comprehensive introduction. It's would be fair to say at master student level. From the other hand, it never hurts to listen to things which you already know, and perhaps even experienced researchers can see some new facets in old known things them listening to my outline. Right. So what would be the plan for now for this lecture? I will start with basic properties of superconductors, of course, and I will talk at large about Andreev's reflection, which, if you ask me, is the most illuminating property of a superconductor, and all other properties kind of follow from that step by step. So we will talk about Andreev conductors, about conversion of electrons to holes and vice versa. We will talk about a contact between normal metal and superconductivity, and under them I will go to Josephson effect, looking at the contact between the superconductors, finding bound states, Andreev bound states, and then in the second half of the lecture we will talk about Josephson effect. At classical level, quantum mechanics is yet to come. In the end of this lecture, I will talk just a little bit about Coulomb blockade, also classical Coulomb blockade, and only by combining these 2, Josephson effect and Coulomb blockade, we finally come to superconducting quantum mechanics. Very good. I would love questions. I would love questions to the chat. I hope I will be able to see the chat. And please don't hesitate. It will be also enormous help for me to tune to the audience if you ask these questions. Good. So let me start with very basic properties of superconductors. And the main property of superconductivity is that it came to our knowledge as something like it is impossible. It was impossible to predict superconductivity. Nobody ever had such a fantasy. Right. So this discovery of superconductivity has been taken place in Leiden, just very near to the place I'm currently in very close to Delft, by Professor Cameron Onnes many years ago. But the legend says that the real discoverer of superconductivity remains unknown. How come? Professor Cameron Onnes was a pioneer of low temperature techniques. And that worked like that. He wanted to get liquid helium, so he got a system of pumps, sophisticated pumps, which pump it for a couple of weeks in order to produce a couple of buckets full of liquid helium. After that, he had to do experiments. He wanted to do many experiments because he was pioneer. And before helium is evaporated, he had only a couple of days. So he desperately needed hands. He did experiments by himself. All assistances, all PhD students have been involved. It was not enough. So what Professor Cameron Onnes did, he went to crossroads of Leather City. He saw teenagers hanging over there without much to do. And for little pennies, he has invited them to the lab to do these experiments. And once upon a time, while supervising such a young man, he has discovered that an expensive device ohmmeter has been broken as a result of apparent negligence. And when measuring resistance of a sample versus temperature, resistance just dropped to zero, apparent shortcut negligence. So this teenager has been sent away without pain. He was a real discoverer of superconductivity. Well, professor was diligent enough to repeat the experiment, and it turns out that resistance of mercury at certain critical temperature just got to zero, not to some negligible value, just to zero. That was unexpected, that nobody could imagine or predict. But yeah, that appeared to be experimental fact given to us. Very soon, another basic property of superconductivity has been discovered, Meissner effect. It turns out that magnetic field is expelled from a superconductor, which means that if you put it into a magnetic field, there are persistent supercurrents along the surface of the sample, which completely screen out the magnetic field. Persistent currents, superconductors can have currents without any dissipation, electric currents. And it took a while before superconductivity has been finally understood. Not really very surprising because, yeah, it was unexpected. Nobody could think of it. Nobody could predict it. Theoretical physics is very powerful science, but it's not really about predicting totally, entirely new things. So it took almost 50 years before the superconductivity has been understood. It was the age of very fast, intensive development of physics in general. Well, still, it took that much to understand what is going on. Right, so now I'm at the stage of repeating a very popular cartoon, about superconductivity, which has approximately the same relation to reality as this picture to processes of human multiplication. Nevertheless, it works. That's important. That's why everybody cites it. So what does this cartoon say? Electrons are attracted by some reason. They form pairs, Cooper pairs, with zero total spin, but with total charge of 2 electron charges. And they're composed of two fermions, or for the bosons, and they form a bosonic condensate. A bosonic condensate, a macroscopic quantum state where all Cooper pairs, one of those are kind of collectivized, and that macroscopic state is characterized with an order parameter, which is complex, which has phase. And this is an example of spontaneous breaking. Spontaneous breaking of a symmetry one cannot imagine to break. Spontaneous breaking of gauge invariance. In short terms, it means that one of the most fundamental laws of the universe, charge conservation, ceased to work in superconductors. No wonder it was quite an unusual concept. That was discovered, that was formulated in microscopical terms by Martin Cooper and Schrieffer. Several years before that, Landau and Ginzburg have invented phenomenological theory of superconductivity, and they did everything possible from these bright minds to make it gauge invariant. That didn't work. That was the first manifestation of this strange phenomenon. Going a bit too far, this spontaneous breaking of gauge invariance, together with several additional things, eventually makes it possible to make artificial quantum devices, artificial atoms, to have quantum mechanics at home with superconductors. Right, that was the basic properties I needed. I still don't have any questions. Well, I don't know. Perhaps it's all known, perhaps it is not taken. Let me go further. I'd like to talk about a spectrum of charged excitations. I forgot to say that all superconductors are metals in normal state, but well, let me do it now. And let me first describe the spectrum of charged excitations in metal. Well, perhaps I could start sketching a parabolic spectrum in metals and remind that the states are filled up to some energy, Fermi energy. And what is interesting is going on at low energies counted from Fermi energy. So somewhere here. Then I do quite simple thing. First of all, I recognize that if the state is empty, like above Fermi energy, I can add an electron. If the state is below Fermi energy originally, somewhere here, I can extract an electron. So in fact, we have two completely independent branches of charged excitations. Electrons and holes. And owing to charge conservation, they are completely independent. They cannot talk to each other. They could not even know about each other. Also, what's important, in principle, it costs no energy to create such an excitation. You can create electron-hole pair and to go to other quantum state, paying almost no energy. Properties of normal metal. What would be a difference if we come to superconductor? If we recognize that we have a condensate of Cooper pairs, which in practical terms means that we can create a Cooper pair or extract Cooper pair without paying any energy, without even changing the state of this condensate. All right, what do we expect? Suppose initially we have a hole here, and what it can do is to absorb a Cooper pair from this condensate, then it becomes an electron. If it is an electron, it can damp Cooper pair to condensate. Again, it doesn't cost any energy. It brings the system to the same state, but electron excitation has become a hole. So electrons and holes are mixed in superconductors. And the spectrum, as a result of mixing between two levels, anyway, in any case, when we are talking about two levels which can interact, overlap, they repel each other. They repel each other, and that gives rise to a gap. That gives rise to gap in superconductor spectrum. So we have such a transition, such a qualitative change of spectrum. Right, and the excitations here are quasi-particles. They're neither electrons nor holes. Those are superpositions of the states. Well, apparently at this side, they're close to electrons, and at this side, they're close to holes, while precisely here, excitation with minimal energy is equal weight superposition of electron and holes. And there are no excitations at energies smaller than this superconducting gap. And again, it's another property of superconductor which is very important for applications of superconducting hardware. Right. Perhaps I have to mention at this point that there are superconductors without the gap. Those are exotic superconductors, but also usual superconductors, which are deteriorated by magnetic impurities or by significant current, which goes through. There is superconductivity without the gap, but in most applications, it is very inconvenient. Why is it true? Let me again say it a little bit in advance. Well, that gives a possibility to create many different excitations, paying no energy for that. And this is usually dreadful for quantum applications. Fine. So that was about bulk superconductivity, and that's about everything which I wanted to say about bulk superconductors. If you have any questions or answers, please don't hesitate to use chat. I hope I see chat. If there are questions in the chat, I don't see them, please let me know. Right, there's a question. Why do you call Bose condensate since electrons are related to Fermi statistics? Maybe due to the fact that value of total spin projection is 0. So this is, people talk about Bose condensate of Cooper pairs. Cooper pairs are composed of 2 electrons. If you add 2 fermions, you end up with a boson. And these bosons can condense. I need to mention that it is still a cartoon, although very popular, which means very adequate cartoon, but still a cartoon. It implies that electrons first form Cooper pairs, and then these Cooper pairs condense. In fact, it's all correct, except the fact that there are no Cooper pairs as independent particles, at least in usual superconductors. In fact, all Cooper pairs only exist in this condensate. All right. I hope this answers your question. And right, let me do something practical. Let me do some experiments with superconductors. And what I want to do now, what Professor Andreev theoretically predicted quite some time ago, is the following. Let's have normal matter. So electrons at holes and holes at any low energy. Let's have superconductor on another side. And right, we need to connect somehow these two. Let us connect it with ideal nanostructure where particles can go from the left to the right, from the right to the left without any reflection, like ideal interface. This is, of course, idealization, but first, it's very useful idealization. Second, we can easily, apart from this, and see what would be more involved situation. All right. So what was a paradox? Professor Andreev addressed once. Suppose the energy of incoming electron is smaller than this delta, is smaller than the gap in superconductors. Right. And it goes to superconductor, the point that it cannot appear in superconductor. It doesn't have enough energy. The only possible evolution of this electron is to be reflected, since it cannot be in a superconductor. But it cannot be a usual reflection because nothing in this structure can reflect this electron. So this is very special process of Andreev reflection going on. This is for energies below the gap. With energies above the gap, still there is some probability there is this process of Andreev reflection. Why? As I mentioned, electron charge excitations over here are not precise electrons and holes, they're superpositions. So in any case, they don't match incoming electron. Good. Andreev reflection. What is this? Right? That's perhaps most of you know. An electron is reflected back to normal matter as a whole. And this is eventually the only possibility. Let us check, if we're not crazy, let us check if fundamental conservation laws are obeyed in the course of this process. All right, what about energy? Energy is conserved, so a hole which is reflected from superconductor has the same energy as incoming electron. Charge, first of all, it doesn't seem to be conserved, right? We have electron with a negative charge and we got hole with positive charge. What is going on? The Cooper pair goes to superconductor. So the total charge is conserved. There is a transfer of charge to the superconductor at each Andreev reflection process. Conservation of momentum. If there's really no reflection, momentum is conserved as well. Although velocity of the object flips because, well, one can see a hole as an electron which is propagating back in time. Spin also is conserved as well because the spin of Cooper pair is 0. Good, Andreev reflection. Let's see how I'm doing in time. Yes, I need to accelerate a bit. Let me write more formulas about this because the formulas is interesting here. What was that? We've been talking about electrons and holes as particles, but they are waves. They are waves, and if electron will become a hole, it means that this wave eventually has two components, electron component and hole component. Let's see, there is a question. If the excitations that we were looking at in the superconductors are superpositions of electrons and holes, should they have no charge? Then how can we say that we conserve charge pumping a Cooper pair? All right, 2 questions in one. Excitations are superpositions of electron and hole indeed. They have indefinite charge. It means that they have probability to have negative charge and corresponding probability to have positive charge. How can you do this? You can think of extraction of this quasi-particle to normal metal. And then with some probability it appears there as an electron, with some probability it appears there as hole. That's about excitations. As to Andreev reflection, in its most conservative presentation at energy smaller than delta, it does not involve any excitations in superconductors whatsoever. That's important because there's no energy to produce this excitation. And the only change of superconducting state is an addition of Cooper pair, which, as we learn, does not change superconducting state, but just increase its charge by 2 electrons. All right, I answered your question. If you have something more, please repeat it. Good. I want to talk about the waves a bit. We talked about particles, let me talk electron holes, about the waves. Right, so we have two-component wave function composed of electrons and holes. And an analog of Schrödinger equation for this situation would be celebrated Bogoliubov-de equation. Not these guys really collaborate, but kind of equation has 2 names on it. What is this? There is a couple of usual Schrödinger equations for electrons and for holes. For holes, energy goes with minus sign because I inverted in time. That's okay. And there is strange potential which couples electrons and holes. And that exists only in superconductors. Yes, of course, it is what we discussed. Something which provides transitions between electrons and holes and back. Right. So that's analogous to Schrödinger equation. One can kind of solve it and one knows everything. Let me talk about less obvious consequences of this equation. It turns out that if the hole is reflected from superconductor, it is not reflected like we expected at incident angle. It really follows back all the trajectory of the incoming electrons. So suppose we have a source of electrons here, and they propagate in some scattered media, which is practical case. Actual metals have plenty of scattering effects. Right, and it scatters many times before it gets to superconductor. And wave reflection has happened. And surprisingly, the reflected hole really repeats all these wiggles, all the scattering events, and is focused back on the same electron. At least if the energy of this electron and hole match Fermi energy precisely. So in fact, Andreev reflection is a realization of a magic mirror of this kind. A mirror which cancels scattering, which could happen in front of the mirror. Good. That was about electrons and holes as waves, as coupled waves. Let me go further. If we understand that we are not dealing with particles, but with the waves, we understand that we miss some important characteristics of this reflection. Well, for particles, it wouldn't exist. Electron goes to holes. If we are talking about the waves, we also have reflection amplitude, phase shift between incoming electron wave and outgoing Hall wave. Right. I don't want to talk much about interesting process of conversion of electron to hole inside the superconductor. Although it is important to say that it doesn't occur instantly, whatever, at a space of several atomic layers, which one might think. The point is that energy scale involved with superconductivity is very low, and it takes quite some time and distance for electrons to interact with superconductivity. So, in fact, in superconductor, one sees exponential decay of electron and wave functions, which occurs at some microscopic scale under practical circumstances. It could be like 50, 100 nanometers, even in a dirty material. Right. What's important for us that upon this reflection, electron wave acquires a phase vector which contains superconducting phase of the slit, not very surprising, and also it has energy dependent factor. This energy dependent factor will become important when we look at bound states in superconducting contacts. All right, Andreev reflection amplitude. And let us see what perhaps I dare to, to formulate control questions. Let us now consider non-ideal nanostructure, which means that there is a reflection at the nanostructure itself. We are sending an electron to superconductor. So it has some amplitude to be Andreev reflected as a whole, but also there's some amplitude of normal reflection. Right, so there is an incoming wave, there is a current associated with this incoming wave. If there's no any reflection, then the current is 1. It's in certain units. Control question, what would be the current for this situation if the total current is 1? I know that organizers would easily answer this question, but I would rather think of participants. Who dares? Let me help a bit. Let me forget about fancy Andreev stuff. If you just have an electron come into something and it experiences a normal reflection, so what would be the current? Instead of 1, part of the electron is reflected. So we find here reflection amplitude. I have to square to get probability. Okay, that's for normal reflection. That's something we I need to do to take Andreev's reflection into account. What is this? Who can help me with this? It might be just good. Oh yeah. Yes. Add a negative term containing the whole being reflected. Another version, if it's normally reflected, that would be no current. If it's transmitted, the per electron current is to E times transmission rate. Yes, everything is fine. I'm happy. You got the point. One has to account for another type of reflection, but not to forget that the hole has opposite sign of charge. So to account for opposite sign, I put plus here. Suppose Andreev reflection is ideal. The current is 2. So if there's normal reflection, if there's no normal reflection, the current under the gap should be doubled. It's like, advertisement in cheap supermarkets. Perhaps you have seen one. You get 2 things, you pay for 1 thing only. Fine. I guess we got through all right. I have to go on. And let me talk about a little bit more complex situation when we don't have this ideal reflection, which we have when we have scattering somewhere at the interface at the contact between normal metal and electron. I can generally say, well, I just put nanostructures. I put on a structure, and for simplicity, I concentrate on a single transport channel in this nanostructure. And let us see what can happen, which process, which transport processes can happen in this situation. Basically, the sketch here. First process, electron goes through nanostructure, get the superconductor, get Andreev reflected, and comes back as a whole. That doesn't exhaust the possibilities. Here, it comes back as a whole, and the whole is reflected from this nanostructure. It's reflected back. It has a second chance to be Andreev reflected. And finally, it leaves it. Those are amplitudes of different scattering processes. And since the amplitudes, one has to add them to get the total amplitude of Andreev reflection. All right, so what is important here? Scattering matrices for electrons, for holes. Since again, a hole is an electron inverted in time, I need to replace all amplitudes with complex conjugated. And I have to take Andreev phase into account. Now I am ready to do simple algebra. Very doable. You could do it at home without any hesitation. Let's see what is going on. First term, transmission amplitude for electrons, phase factor of Andreev reflection, and transmission as a whole conjugated. More complex process. You have two normal reflections, 2 Andreev reflections extra. This gives you a factor. For the next term, you just have a square root of this factor. Yet another term, you have third power of this factor. So in fact, you have geometric series, which you can sum up to this. Here we have capital T's. It means that instead of transmission amplitude, we have transmission coefficient. Amplitude of Andreev reflection is proportional to transmission coefficient because it involves already 2 particles, electron and hole. Fine. So that describes peculiarity of Andreev reflection. What I found especially illuminating, that this does not depend on superconductor whatsoever. It all defined by properties of normal transport, so the contact between normal metal and superconductor, which is very important facet of superconductivity. Okay, let's see what's going on. Well, we kind of simplify this formula. We go at 0 energy, where these phases are just pi over 2. Right, and we got the terms of Andreev reflection expressed in terms of transmission coefficient of the structure in normal state. So let us see. It is small if transmission coefficients are small. If transmission coefficient is 1, it is 1. The Andreev reflection for ideal nanostructure without reflection, transmission coefficient 1, is 1, complete Andreev reflection. Let's get to conductance. Let's get to what's called Andreev conductance. We have an analog of Landauer formula. For Landauer formula, in order to get conductance, you have to add all transmission coefficients, multiplying it with conductance quantum, amount of conductance per each transmission channel, and summing them up. Good, so that's what we have for Andreev reflection. Not to forget coefficient of 2. This is Andreev conductance in terms of transmission coefficients. Let me look at limiting cases. If all transmission coefficients are small, then our contact is in fact tunnel junction. We have a potential barrier between 2 metals, and we have kind of bad low transparency per each channel. Good. In this case, it is sum of squares of transmission coefficients versus sum of phase powers. So eventually for tunnel junction, Andreev conductance is much, much lower than conductance in the normal state. Let's take quantum point contact where transmission is ideal. And as we discussed, the conductance is just doubled. Right. For more complicated cases, we need to use transmission distribution. We need to understand what is the frequency of transmission coefficients, what is the probability to have transmission coefficient in a given structure. That's a separate problem to look at. There is known answer for diffusive conductor. And surprisingly, for diffusive conductor, we have no sign of superconductivity at low temperatures. was experimental work which was a bit unexpected and was even misunderstood. But in fact, that's accurate prediction of theory for a diffusive conductor, no tunnel barriers, no ballistic transmission. Andreev conductance and normal conductance are the same. Right. That was about a contact between normal matter and superconductor. Let me go to the business. Let me go to the most frequently applied concept in quantum superconductivity. Let me get to Josephson effect. I will talk about this in general. I will talk about two superconducting leads which are connected by some nanostructure. Right. There can be phase difference between these two superconductors, and in the contact in superconductors we expect persistent currents which are property of the ground state, which go on without any dissipation. So that we have, and this current has to be periodic in terms of the phase. Why is it so? Because superconducting order parameter is this function of the phase. You add to pi, you get precisely the same state. Current has to be periodic. And this is called DC Josephson effect. Nowadays it's almost forgotten, but Josephson is eventually a person who discovered the effects at very early stage of his career. Right, so this is DC Josephson effect. Current at constant phase difference. AC Josephson effect, if you ask me, is even more spectacular. And it tells you incredible thing. It tells you that superconducting phase is in fact voltage, or in more exact terms, the time derivative of superconducting phase, whatever you do, is the voltage applied to this voltage difference between these two contacts times 2e divided by h bar. Right? This is a consequence of this gauge invariance, if you wish, of this broken gauge invariance. What does it mean? It means that if you apply constant voltage, you got AC current. You got AC current because the phase will be a linear function of time by virtue of this relation. And the current, because it's periodic, will just oscillate harmonically with this frequency, which is called Josephson frequency. That's Josephson effect in short. Let me tell you one thing. Kind of, it's easy to accept and believe, but it's better if you just derive it with your own hands without any assertion. Let us understand the link between Josephson current and Josephson energy, phase-dependent part of the energy of the structure. For doing so, let us change the phase slowly and look at corresponding energy change. Right, energy change. In any case, just by electricity theory, it's current times voltage. All right. This is voltage by virtue of Josephson relation. This is a current which depends on phase. From the other hand, the time derivative of energy should be time derivative of the phase times phase derivative of energy. Okay, this means that the current is derivative of energy with respect to phase. Just thermodynamic relation always works. Let us see how we can assess wait a second. Am I beyond the time?
Yeah, you have a lecture time until 12. It's
oh, sorry. I just yeah. I forgot. Okay. I have still plenty of time. Sorry, I was a little bit confused with this different time zones. All right, Josephson contact. Let us understand it in terms of Andreev reflection. How to set it? Well, we have a structure just in the middle between two superconductors. And what do we have on both sides? We have incoming waves and outgoing waves. And the scattering matrix of this nanostructure eventually does what it does usually. It takes incoming waves and transforms those into outgoing waves. That's what I get. It does it separately for electrons and for holes. Yeah, so there are electrons, waves coming from the left to the right. There are Hall waves coming from the left to the right. And all of them are transformed into reflection waves. Well, shortly one can write it as a matrix with two blocks, electron hole block and Hall block. All right. What happened next? They experience Andreev scattering at the boundaries of a superconductor. And in this case, you kind of close the loop. All outgoing particles become incoming particles, and they are transformed into holes, and they pick up coefficients we have discussed, amplitudes of Andreev reflection. Good. How we can comprehend this? Basically, it never works. At arbitrary energy, at arbitrary circumstances, it would never work if we wouldn't have solution to these questions. But sometimes we do. So we take outgoing amplitudes, we Andreev reflect them, we normal reflect them, and we get the same wave again. There is a solution. Okay, in terms of matrices, it means that the product of these two matrices has a eigenvalue 1. which is not common. But we have a parameter to tune the energy of the state. And Andreev reflection phase does depend on this energy, which makes it there is a chance to make this happen by changing energy. Right? So what does it mean? What we have discovered? It means that in a nanostructure, if there's phase difference applied, there is a bound state, bound Andreev state, kind of standing wave function, which is composed from electrons and holes at certain energy. Here, there is the energy of this Andreev state. We have single Andreev state per quantum channel. And this is the energy at different transmission coefficients, T, and different phase differences. Right. So if we, again, about ideal nanostructure, then the energy, well, it starts at delta. Delta is the upper bound for all bound states. We have continuous spectrum starting at energies delta. Okay, it starts at delta at zero phase, and then it just dies very deep up to zero, down to zero. And then it returns again. Anyway, it has to be periodic function of the phase. This is for ideal transmission. If transmission is low, well, you've got a bound state which doesn't depart much from the edge of continuous spectrum, but still persists, still depends on the phase. All right. So by any nanostructure, by virtue of Andreev reflections, we have, strangely enough, in superconductors, we have localized states. If you have heard about semiconductors, about the efforts which they put in order to get quantum dots by tuning barriers, confining, making heterostructures, they have tremendous difficulty to confine electrons in quantum dots. Well, they know how to do this, they success. Surprisingly, superconductivity provides much more convenient facilities for localized states. Just take two superconductors, bring them together. There is a big chance to have bound states at each contact. All right, that was about bound states. Let me recall that for Andreev, for Josephson, the most important part is energy. And right. Okay, I recall that most of you are not students, therefore not to be cheated. Right, that's very important calculation which required some cheating. Let's see if you are able to detect it and to put questions. Good, we have computed the energy of Andreev bound state. We sum up these energies. Okay, we've got the total energy of the junction in the ground state. And that we can do, that we can utilize to evaluate the current, the superconducting current, get Josephson energy, all stuff like this. So who can tell me where I have cheated now? I never thought I'm a good teacher, not a teacher. I never thought that I'm a good cheater, but apparently it is. So who can tell me what's the mistake with this? All right, this energy is positive. This is the energy of excited state. I have an state with some energy smaller than delta. This is excited. This excitation never happened. I'm talking about the energy of the ground state. So what I have to do, and this is a little bit non-trivial point, which is frequently misunderstood, but this is kind of prescription what I have to do. I have to take this energy excited state with a factor of 1/2 and -2, and that will be modification of the ground state energy. That's what I did. And factor of 2 has disappeared when I take into account 2 directions of spin for this state. All right, that was the calculation. Josephson energy. Function of phase. So we can make a current does that. I differentiated this. Sure, I have different current phase characteristics. At small t's, the current is small, but it's pretty much harmonic. I could just neglect this denominator. At ideal nanostructure. Let's see. That's what I have. It's actually sawtooth function. Goes like this and then drops suddenly and repeats itself. But this is supercurrent for a system of quantum channels in its dependence on phase. DC Josephson current. So what do we do? Historically, Josephson junctions, and it was so for almost 40 years. Historically, all junctions have been tunnel junctions. Simplest way to produce a junction, you take a metal, you oxidize it. If it's aluminum, it's native oxide level, which stops. Put another superconductor, you got nanostructure, you got tunnel barrier. For tunnel barriers, there is a very simple consequence of this formula. Sinusoidal dependence of current upon phase, and the coefficient is exactly conductance of tunnel conductance in the normal state times delta with some coefficient. For energy, Josephson energy comes with cosine phi. Josephson energy is proportional to conductance, proportional to the gap in the superconductor. Again, we have combination of normal and superconducting properties of the scatter, used to be called a Barata formula. Good. Classical dynamics of Josephson junction. What's important, the Josephson junction is intrinsically a part of electric circuits. So if I want to understand the dynamics of Josephson junction, I don't have to know anything but elementary theory of electric circuits. Let's have it like this. So there's a Josephson junction. I want to bias it with a current. And I want to have a capacitor in parallel to the junction. And, well, a resistor. Resistor is important for me. It brings some dissipation, some friction. Well, otherwise I would have to deal with a system without friction, not very safe. So, how to describe it? Well, as nothing involved, but current conservation. The total current is a sum of three currents through Josephson junction, through resistor, through capacitor. Remember, current still run through the capacitor if voltage is a function of time. Good. I need to recall Josephson relation and relate voltage with a time difference of the phase, time derivative of the phase. Take this and put it a little bit dimensionless form. So what I did here, I introduced time scale, which is made out of critical current, so that inductance and capacitance, which is called plasma frequency in Josephson junction. And resistor works as a damping for this nonlinear oscillator, damping with some quality factor made of resistance. Let me draw it. Let me draw it. This is a device which gave a name to this model, the model of washboard potential. I've seen this device once in my life. It was like 50 years ago. Who has seen it in more recent times? Please give it to the chat. I guess it's still produced, but I've never seen it put into practice. Good. Good. Fine, that still exists, very practical ones. Right, so it is a model of tilted washboard potential, which has been very popular in physics of Josephson junction. From this, you could figure out when Josephson physics has started. It was still in times where you can readily see such devices. Origin of all quantum devices, in fact. So it looks like a motion of a particle in a potential which comes from Josephson energy, cosine of the phase, and current, which tilts this potential and makes it washboard potential. Right, so one can get lots of intuition about Josephson dynamics, just considering the motion of particle in such washboard potential. Good, let me immediately give you a simple answer concerning the critical current, so the tilt of this potential. Right, so if tilt is small, then the particle just stuck in one of the minima of this potential, which means that there is no motion of phase. Therefore, there is no voltage at Josephson junction. Zero voltage state at finite current. But if you increase current, this minimum will disappear at some critical point. And at the bigger currents, you just don't have any equilibrium point in this potential. So the particle would go down. There will be average time derivative of the phase. There will be average voltage at Josephson junction. Fine. I'm done with Josephson junction, and let me talk about switch the topic completely. I still have 7 minutes for this. Let me talk about Coulomb blockade. No superconductivity, normal metal, no even leads at the moment. We just take a metallic island and we hang it somewhere in vacuum. The message is that if this island is isolated, its charge is quantized. Eventually, if you think of this word quantum mechanically, it would be a difficult message to accept. One could think of superpositions, but believe me, all superpositions disappear if you isolate this island accurately. So there will be quantized charge of this island. Perhaps somebody can recall Millikan experiment where this was a first observation of quantized charge has been done in more or less the same manner. What's important for me that this costs charging energy. How come? Well, if you put a charge into metallic island, it will go to the surface. There will be electric field around the island. This electric field will cost energy. Well, without going to any details, this energy can be presented as a capacitance of this island. So electrostatic energy is charge squared divided by 2 capacitance. Electrons are quantized. So charge is electron times integer number. So I can write it as some energy scale times squared of energy number. The question is this the same as a second quantization in quantum mechanics? No, not yet. We will talk about second quantization. Now we are talking about charge quantization, which is by chance, is completely 100%, 1000% classical concept. Charge quantization just means that particles, elementary particles, can be counted with our fingers. And in any isolated object, there's only integer number of particles which we can have. What's important, it costs charging energy, some energy scale made from charge and capacitance times and squared number of particles. Let me do important estimation. Let me compare this with quantum energy scale. There is an island it is isolated finite volume, and there will be finite level splitting of electron states in this volume. To make long estimation short, charging energy is much more important than this level splitting. For realistic Coulomb islands is a factor of 10 to the 8 in magnitude. So the charging energy, in fact, is much more important than any kinetic energy of the electrons in this situation. And this explains the name of Coulomb blockade, or nickname, whatever you say. Transport is blocked if you cannot really supply this energy. If you cannot supply energy to charge your metallic island. Right, let me just quickly flip. Perhaps we we will start the second lecture with this. Let me just quickly flip a device with which one can study this charge quantization. It's not very practical to hang these islands in vacuum. Let's put it on the substrate. Let's put this island on substrate. We want to change the number of electrons in the island, so let's put some metallic electrode nearby. Right, and there's still possibility to tunnel between metal and island. I need some tool to energize this tunneling, so I put some gate electrode, and the rest, I believe, you will hear in